that gave us the exact same functional code coverage as all those 19,000, and then went and put those into the fuzzing process. And what that allows us to do is be that much more efficient about the fuzzing that happens. The second one was, fuzzing was really the first part. Fuzzing was something we did across the board. If a target was particularly difficult or it had multiple issues that surfaced, we went and applied security experts to go do a security code review and detailed program analysis on it. And so they would actually have a method using SAL to annotate the entry point to the parser and then iteratively go through the set of function calls and declare where that input was validated. And so now you have an attack path in the code base. And the tools, what we could do with our tools is crank up the noise level like never before to go analyze the set of code in this attack path. And this is, we could crank up the noise level to a level that was, frankly not sustainable code base wide, but for an attack path was. And the other thing we could do was take our mitigations and emit them more aggressively in the attack path for these parsers. So the third part of the strategy was to go take security experts, members of the security research community and internal product experts on security, and go apply them to the attack surface of the product. So we started off with feature reviews. So we prioritized all the different features of Windows Vista by risk. So we looked at what's on the network and what takes anonymous input and what makes security guarantees and what's had a history of bulletins and whatnot before. And we prioritized that list and had a feature reviewer go and sit down with the team, or in some cases multiple feature reviewers, and look through their threat models and look through their design and their attack surface, understanding were they using these concepts and doing it well. And if there was an area that was weak, we went and referred it to penetration testers for deep inspection. We augmented, as I mentioned, the internal reviews with security consultants. There was really an unprecedented amount of security review by external security consultants on Vista across the board in Windows Vista. We tried to pair up their particular expertise with the components that they were reviewing. Each of those security consultants had a Microsoft full-time employee who was their driver, and this person would act to unblock them if they got stuck, help them with the overall Windows machinery and the Windows process, and kind of help them be more fluid through the system. So feature reviews, if feature reviews are kind of, you go to the doctor and he gives you a basic checkup. Penetration testing is more like a body cavity search. When I used to talk about this, I used to call this the largest pen test in history. And people that used to work for the government would remind me it's the largest commercial pen test in history, We have an internal team of hackers. I don't know, you may remember the LSD folks, last stage of delirium, that discovered the flaw that the blaster worm exploited. Those are people on my team and are members of this internal pen test team. We also have multiple simultaneous pen tests going on, so not just stuff that we were coordinating, but other things that teams had taken it upon themselves to go get pen tested. Monasano looked at the NetIO stack, for example. And then we had what we call our blue hat hackers. And so Jim Alchin gave them this name in some press article. They really hated it, and so naturally the name stuck. And these were over 20 different security consultants, basically in one or two rooms. And it's really like kids in a candy store here. They had full access to source code, full access to private symbols, specs, threat models, the whole thing, access to product development team. Every question they ever had could be answered within a one building radius of where they were. I mean, if you think about it, if you go and pen test Windows Vista, if you have a question about the kernel, the stack, the heap, the service, RPC, DCOM, all that stuff is really within about 300 feet plus or minus where these guys are. The basic approach here was we went and selected targets based on a variety of different inputs. One of them was things that came back from the feature review process as needing further scrutiny. I kind of mentioned this earlier, but it's an important point that penetration testing is fundamentally a diagnostic process. You will never take pen test and go secure your code base with it. It can only tell you kind of as an instrument what is going on and identify a pattern of defects or a set of assumptions that were potentially dubiously made. And then you have to take that information, fix whatever bugs it finds, but then drive remediation in the engineering process to go improve that. And so they'd spend anywhere between a week or 2 months depending on the complexity and the size of the target. And one thing about pen testing Vista is absolutely nothing was out of scope. So for these guys, this was quite a bit different than normal penetration testing that they do for other customers or even other components inside of Microsoft where they say, you know what, I really don't want you to find bugs over there. I really want you to find bugs over here. And if there are bugs over there, I really don't care. I want you to find bugs here. In Vista, it was go everywhere and find all the bugs you absolutely can. So that was really a neat experience for them. This is some sampling of the findings that were found through this process. One thing we found is that the process tended to yield what we call rabbit holes. And what I mean by this is you sit down with a team and you start to whiteboard their component, and it turns out that component's actually not that interesting. But they have this dependency on a component, and that dependency is really interesting. And so this kind of iterative, recursive, kind of drilling down through dependencies is something that would happen quite often. The next kind of thing that these consultants would find are contradictions in assumptions, things that couldn't possibly hold valid. So, for example, in one threat model they found there was a component that took data off the network. It didn't actually parse that data, do anything particularly with it. The data was actually fully opaque to it, and it just passed it off to the next guy downstream. And so it said, well, you know, we don't have to do any particular hardening or what have you, because we actually don't do anything with the data. The next component of the line says, we get our data from a local system service, and obviously he's not going to try to hack us, so we don't have to do a lot of validation on the data that we get. Clearly, somebody's got to do the security work here, and so this is the kind of you know, inter-team or inter-component dependencies that would surface through this process, and we'd say, okay, somebody's got to do the validation here. Another thing they would find are what I call process handicaps. These are things that in a large release, somehow a product team or a component team ended up getting disempowered because of the overall process or because of the cycle or what have you. And so, for example, a small team who wants to make what to them is a very large change might say, well, geez, I don't know if I can go to the Windows ship room and get them to support making this change at this late stage or right before beta or what have you. And we said, no problem, we'll talk to the ship room guys and get them to approve it. And so this was a really nice partnership that we had where teams that ordinarily would have maybe a small voice or have difficulty fixing things, we could actually go help them and drive these things and get them fixed. We'd also encounter what I call failures of imagination. There was one particular case where a component had a particular attack. There was a man-in-the-middle attack on their component. And they thought, well, this attack is really complicated. You know, you'd have to somehow get packets at the right time and really be at the right place to actually, you know, exploit this. And so we don't really think it meets the bar for fixing for Vista. And we said, you know, this absolutely has to be fixed. You know, some of us lose sight that all the people in this room, we're all versed with security. We deal with it on a regular basis. And the developers at Microsoft, though all of them go through security training, maybe the focus on their job is making it so that blind people can use the software. Or people that cannot hear can use the software effectively. And that's really what they think about first and foremost in their mind, their customer and how to do that. And so they're not exposed to all of the, you know, the Metasploit talks and all the other great talks here. And so these failures of imagination are a thing that we would encounter. And so one great thing that we got out of having the security consultants here were Chris Padgett and Dan Kaminsky went to this team and gave them all of the software that they could use to repro a man-in-the-middle attack. And so they gave them a server and what have you. And while this conversation between myself and the team was going on about this bug, the product unit manager for that team comes back to me and says, you know what, we took that repro and demo code and we reproduced it in our lab, and it turns out that man-in-the-middle attacks are really easy to pull off. I don't think they should be this easy to pull off. You know, of course we're going to go fix this bug. And so not only did we get the bug fixed, which is great, but it was really a nice collaboration between helping really open the eyes of a team to something that they thought was hard or complicated or they didn't understand in a concrete way and show them in a very personal way. We got an email from a friend of the SWI team, if you will, Matt Conivore, who installed the earlier beta of Vista and said, I noticed there's this file on my system that has owned in the title of it. Is this for real or did I just get rootkitted right away? And we went and looked, and sure enough, there is a DLL in Vista that has owned in the title of it. And we went back to the team and said, what is this about? And they kind of looked at us rather quizzically and said, well, it's the WinLog on Session Viewer Window Hook DLL, of course. That's, of course, the name we would put with the DLL. This was something one of our code auditors found in the code base, looking at the code. This is what he had to say about it. This was found by Felix von Leitner. The funny thing about this code is there's not a single security defect in this line of code. Unfortunately, it took Felix like 2 to 4 hours to figure that out. And Dan Kaminsky, he went to the product team during one of the talks. He says, please, please do not write code like this. Please, please. It's a DOS attack against the code auditors. A couple of them wanted to really spend their time looking at legacy code in the product. So they said, you know, what are the different ways we can easily identify legacy code in Windows? And so how do you identify code that's been around? And Chris Padgett or Dan, I can't remember which one, came up with the idea of, you know, if we can find old copies of MSDN, you know, like 10-year-old copies of MSDN, obviously that's really old stuff. And if that's still in the product, you know, we really want to go look at it. So it turns out at Microsoft, it's not that hard to find old copies of MSDN. So they just basically called up MS Library and they shipped them every copy of MSDN since 1995. And there were some howls down the hallway when they started looking at the Windows 95 SDK, and this is one of the gems that they found. This is Safe Stir Copy, circa 1995. So we've come a long way here, a long way. The last part of the presentation is really about defense in depth. And so, as you can see, we focused on changing the architecture where we could. We went and automated everything that we could. We applied security expertise. And then finally, we know there will be defects that make it through the engineering process despite our best efforts. Attack techniques always continue to improve and find things that we weren't currently aware of. And so we wanted to embark on an effort to try to reduce the reliability that even if a security bug is there, to either prevent it from being able to be exploited because the firewall is on by default, for example, or to do things like add various cookies and mitigations so that even if it's there, your ability to successfully and reliably exploit it is much reduced compared to past operating system releases. So, for example, one of the things we did, you know, we've shipped this /GS compiler flag in Visual Studio for a few years now, and we shipped the first version and it was worked around. We shipped the second version and it was worked around. And so during the WIDBE release of Visual Studio 2005, we had penetration testers go and sit down with the engineers on the compiler and actually pen test and write exploit code and try to figure out all the different ways that we could go improve that flag. That improved version of GS is being compiled consistently across the code base in Windows Vista. The second thing is we went and the heap was largely rewritten in Windows Vista for a number of reasons, certainly with security in mind. And I'm not going to talk about the different changes. If you really want to dig into the heap, go to Adrian Marinescu's talk later today, and he's going to explain all the different changes in the heap. I will though, talk about one of the specific changes we drove across the code base, which is because of the new architecture of the heap, it has new ways to detect when corruption has occurred. So there's control structures that are overridden or what have you, or cookie values that don't match anymore. And so the question is, what does the heap do when it detects one of these corruptions? And so the obvious answer is, well, just go terminate the process and take it down. And it turns out if you just go turn this on for every app that runs on Windows, a lot of apps just happily corrupt their heap on a regular basis and continue to eke on and function. And it may be the 10th time, the 12th time you start up the app and you're in the middle of your document or what have you, reading your email, and the app goes away and you have no idea why. It's because it's somewhere along the way it blew its brains out. It didn't realize it. It was getting along just fine. And so what we did in Vista was we have this option called Heap Terminate on Corruption. For 32-bit apps, we went and basically turned it on for the entire operating system. For 64-bit apps, this was actually a nice point of differentiation here. So unlike 32-bit apps, on 64-bit, we don't have an app compat problem. We don't have a huge legacy of installed applications on 64-bit yet. And so we can make different choices about security to go set kind of a better precedent for security on 64-bit. So for example, NX is on by default for 64-bit systems and all 64-bit apps. Heap Terminate and Corrupt